So, in the hard case we had the following filters. Analysis. So, this is H 0 and this is H 1. Synthesis. Remember, on the synthesis side, at that time we had said we will allow for a plus minus ambiguity here. Let us keep that ambiguity and you will see why that ambiguity is needed. This is G 0 and this is G 1. Now, let us write down tau 1 z here. Tau 1 z by definition is of course G 0 z H 0 minus z plus G 1 z H 1 minus z, and with our definitions of G 0, H 0, G 1 and H 1, we have the right hand side becoming simply half G 0 is 1 plus z inverse, H 0 minus z is 1 minus z inverse by 2. Now, here we have a plus minus ambiguity. G 1 z is of course 1 minus z inverse and H 1 minus z is 1 plus z inverse by 2. Now, when you look at this carefully, you notice why we want this ambiguity there. We want this to become 0. And therefore, it is obvious that the minus sign should be chosen. The plus sign will not give us a 0. So, for Elias cancellation, it is very clear that G 1 z must be equal to minus 1 minus z inverse and not plus. So, therefore, now let us freeze our G 0, G 1, H 0 and H 1 for the hard case. And now, let us verify the perfect reconstruction condition or verify tau 0 z. Indeed, tau 0 z is obviously G 0 z H 0 z plus G 1 z H 1 z. And when we expand this, we get 1 plus z inverse, the whole squared by 2, minus 1 minus z inverse, the whole squared by 2. and this is easy to evaluate. It essentially gives us half into half and we can use the a plus b into a minus b kind of expression, and we have 1 by 4 a plus b is 1 plus z inverse plus 1 minus z inverse, and a minus b is 1 plus z inverse minus 1 plus z inverse. So, 2 z inverse, and here of course, the z inverse cancels, and here we have z inverse surviving, and all in all this is equal to 1. Simple and elegant. In fact, it is 1, but with a factor of z inverse. So, C 0 is equal to 1 and you have a z inverse there. The tau 0 z all in all is z inverse. What does this mean? Essentially, only a delay of one sample. The constants have already been accommodated. So, C 0 becomes 1. Now, why was this delay required? As I said, this delay is required on account of causality. If we did not want this delay to be there, we would need non-causality either on the analysis or on the synthesis side. So, for example, if I do not want this z inverse term, I must multiply the output by z. In other words, I must shift the output backward by one sample. That means, G 0 and G 1 would now become non-causal filters. Wherever causality is not an issue. So, for example, suppose we are dealing with spatial data, then this is not a problem. We can get tau 0 z exactly equal to 1 without the z inverse term. But where causality is an issue, as it is when you are dealing with time data, then we cannot do this. Now, in fact, in this case, let us also dissect the situation and understand it a little better. Let us put down the condition that we had written for Elias cancellation in the specific and simplest case and see if it holds here. So, indeed, we had suggested that the simplest possibility of Elias cancellation is when G 0 z is either plus or minus h 1 of minus z, and in the Haar case we have h 1 z is essentially half 1 plus or 1 minus z inverse rather, and therefore, h 1 of minus z would be half 1 plus z inverse. So, you will notice that G 0 z is indeed plus h 1 of minus z, but without this factor of half. Now, you know that factor of half is not an issue at all. You remember that more generally we had written down the following requirements. We had said that more generally for Elias cancellation, we need G 0 z to be plus or minus some r z times h 1 minus z and G 1 z to be correspondingly minus or plus r z times h 0 minus z. And in particular, you could choose r z to be a constant. So, in particular, for the Haar case, we have chosen r z to be equal to 2. a constant. And in fact, I can also check for the second expression. G1z in the Haar case should then be minus H0 of minus z, or rather with a factor of 2. So, 2 times, and indeed minus 2 times H0 minus z is minus 2 times half into 1 minus z inverse, which is correct. So, things have all fallen into place. It is convenient. I once again point out how beautifully one can understand several concepts at once when one takes the specific example of the Haar. The Haar MRA embeds in it several concepts explained in a simple way. But of course, we can't be content with the Haar, and we shall slowly understand why. The first step in understanding this is to understand where the Haar is the baby and where we need to grow further. Why is the Haar just the beginning of a family of multi-resolution analysis? In what sense is it the simplest case? Towards that objective, let us look at that low pass filter and that high pass filter from a slightly different perspective. What does it do to a certain class of sequences? Let us see that. So, let us put the following question. What does the Haar do to constant sequences? In other words, consider x n equal to some constant, say C 1 for all n, the extreme case. How would the outputs of the various points in the Haar filter bank look? So, it is very easy to see that if you take the Haar MRA, I will not keep writing the filters again, I will just show them symbolically. I have H 0 here, I have H 1 there, and if I take just the analysis side, it is very easy to verify that the output here is going to be the 0 sequence. In fact, I will take just a minute and verify it. Essentially, H 1 z operates 1 minus z inverse. And this essentially means the operation x n minus x n minus 1 by 2, which is identically 0 for all n. So, this is a very significant observation we are making. We are saying on the Haar filter bank, if there is any constant component in the input, it is destroyed on the high pass branch. This is a slightly different way of looking at the Haar filter bank. In fact, now we will go one step further. In the Haar filter bank, I had one term of the form 1 minus z inverse. Suppose I had two such terms, what would happen? So, let us put that down. So, we will consider a cascade of 1 minus z inverse terms. So, you have a system like this 1 minus z inverse fed into 1 minus z inverse and so on. We shall now prove a very simple and a very elegant result. We shall show that every cascaded, every instance of 1 minus z inverse in the cascade reduces a polynomial sequence to 1 degree lower. So, I am looking at the situation from a slightly different perspective. Now, I am not talking about frequencies or sinusoids anymore. I am saying, suppose you think of an input sequence as having polynomial components. Now, where on earth do you encounter a polynomial kind of expansion? Well, we know about the Taylor series. After all, the Taylor series is essentially a polynomial expansion of an input. And when we make a polynomial expansion of the input and we subject a few terms in this polynomial expansion to the action of 1 minus z inverse, we have an interpretation that we are talking about here. So, visualize a region in which you are talking about the sequence being, and so let the sequence for example come from an analytic continuous function, and let then that function be expanded in a Taylor series around a certain point, which means you have polynomial terms. Now, let those polynomial terms be subjected to the action of this cascade of 1 minus z inverse. That is the situation in which we should visualize ourselves. It is a different way of expanding an input. Anyway, so putting that context in perspective, coming back to the polynomial. So, we will show that if I feed any polynomial of the form say a 0 n to the power of capital M plus a 1 n to the power m minus 1 and so on up to a m, which is a polynomial input sequence. Every time we subject this polynomial to 1 minus z inverse, what is going to happen? So, let us subject it to 1. The first time we subject it, we are doing this. Now, what is happening in this process? It is very clear that when we expand this, the coefficient of n to the power of m is easy to evaluate. It is essentially a 0, I mean you have the term a 0 n raised to the power of m coming from here, and the term a 0 n minus 1 to the power of m, which contributes the coefficient of n raised to the power of m here, and that coefficient is again a 0. So, a 0 minus a 0, which is 0. So, that is interesting. Each time we subject this polynomial sequence to the action of 1 minus z inverse, we are reducing the degree of the polynomial by 1. In fact, let me illustrate this by taking a sequence which is polynomial of degree 1, and let us subject it to the action of this filter. So, you have essentially something like, say, let us take a concrete example. So, let us take 3 times n plus 5 and let us subject it to the action of 1 minus Z inverse to fix our ideas. What emerges here is essentially 3 n plus 5 minus 3 n minus 1 plus 5. And that is easy to evaluate. It is essentially 3 n plus 5 minus 3 n plus 3 minus 5, and that is just 3 for all n. So, you brought the degree of the polynomial down by 1. You had a degree 1 polynomial, now you have a degree 0 polynomial. That is exactly what happens for any degree polynomial. So, what we just showed a minute ago, and I will put back that discussion, is that the coefficient of the highest power n to the power m vanishes. And therefore, when this sequence goes into z raised to the power minus 1 or 1 minus z inverse, so to speak, you only have n raised to the power m minus 1 and lower degree terms left. So, now we have just proved a simple lemma. Each instance of 1 minus z inverse brings the polynomial degree down by 1. So, in other words, in a certain sense, the more 1 minus z inverse terms you have, and by the way, we will soon see these terms are going to be on the high pass branch, not on the low pass branch. You know, 1 minus z inverse, when we substitute z equal to e raised to the power of j omega, vanishes at omega equal to 0. Let us verify that. So, when we take 1 minus z inverse and substitute z equal to e raised to the power j omega, we get 1 minus e raised to the power j omega, and when we put omega equal to 0, we get this is equal to 0. So, in other words, this is 0 DC, so to speak, 0 at 0 frequency, 0 response at 0 frequency. This cannot possibly be low pass in its behavior. So, it must be high pass. In other words, if you do want terms of this kind 1 minus z inverse, they must only be present in the high pass filter. They can't be terms present in the low pass filter. Otherwise, you would have a 0 response at 0 frequency, ridiculous for a low pass filter. In fact, what we are now going to build up is a whole family of multi-resolution analysis, in which you have more and more 1 minus z inverse terms in the high pass branch. And that is in fact very well known as what is called the Dobash family in multi-resolution analysis.